Hello everyone, my name is Abby Daly and today I'm going to be talking to you about hyaluronic acid in wound healing. Throughout this presentation, I will be discussing where you might have heard of hyaluronic acid, how hyaluronic acid is formed in the body, the chemical properties it has, and how it aids in wound healing within our bodies. For those of you that love skincare, you may have heard of hyaluronic acid. It has gone viral many times on social media platforms in the past few years. It is a very popular ingredient known for its hydrating properties, and where we most commonly see hyaluronic acid is in serums and lotions. Some popular skincare brands that you may have heard of are The Ordinary and Good Molecules that make a budget-friendly serum. This is a product that I actually use in my own skincare routine. This form of hyaluronic acid is formed from plant sources through bacterial fermentation. An alternate name for hyaluronic acid is hyaluronin, and it can also be abbreviated to HA. Hyaluronic acid is a polysaccharide that is made up of repeating units of a disaccharide. The disaccharide is made up of monomers of D-glucuronic acid and N-acetyl D-glucosamine. The molecule pictured that is on the right is D-glucuronic acid, and the molecule on the left is N-acetyl D-glucosamine. Before the rings of D-glucuronic acid and N-acetyl D-glucosamine were formed, they started out as linear molecules. The picture demonstrates the mechanism for how each of the molecules turned into ring structures to eventually become hyaluronic acid. In a nucleophilic addition reaction of glucuronic acid, one of the lone pairs on the carbonyl oxygen in the aldehyde grab an H from an acid. In this case, it's HCl. Next, one of the lone pairs on the hydroxyl group, bonded to carbon 5, attack the carbonyl C, in this case carbon 1. At the same time, the pi bond breaks to form a tetrahedral intermediate, with the electrons going to the oxygen with the positive charge. In the last step, the alcohol group bonded to carbon 5 is deprotonated to produce an ether. This overall structure is a hemiacetal defined by the alkoxy group and the hydroxyl group bonded to carbon 1. The ring formation for N-acetyl D-glucosamine proceeds the same way, except that instead of a carboxylic acid, there is a CH2OH substituent, and at carbon 2, instead of the hydroxyl, there is an amide. On this slide, the mechanism for how each of the individual monomers come together to form a disaccharide is shown. This specifically is showing the beta-1,4 linkage between glucuronic acid and N-acetyl D-glucosamine. However, the beta-1,3 linkage would be the same, just at different carbons. The linking of the polymers is done under acidic conditions, with HCl being used for demonstration purposes but not specifically required. The acid is used to first protonate one of the oxygens of the desired alcohol substituents at carbon 1 or 4. Then an SN2 substitution occurs with H2O as the leaving group. Finally, the oxygen is deprotonated by the conjugate base to form the disaccharide. The monosaccharides are linked together by beta-1,3 and beta-1,4 glycosidic bonds. A glycosidic bond is a covalent bond that forms between a carbohydrate or sugar molecule to another group. On this slide is a better visualization of what these glycosidic bonds look like. In the blue color are beta-1,4 linkages, which was demonstrated on the previous slide, and in the red are beta-1,3 linkages. I have labeled the carbons in purple to show where these numbers are coming from. The number 1 carbon starts where it does because when the ring was formed from the linear molecule, that was the end carbon, which would be labeled number 1. Hyaluronic acid is naturally occurring in the body, with most of it being in the skin. HA is synthesized at the plasma membrane by 3 enzymes called hyaluronic acid synthases that are known as HAS1, HAS2, and HAS3. The UDP glucuronic acid and UDP N-acetylglucosamine are added to the terminal end of the growing polymer chain. As the polymerization occurs, the polymer exits to the extracellular space where it can access other cells for healing properties. The three different HAS enzymes are all able to synthesize a hyaluronic acid polymer, but at different sizes and different rates. Research has discovered that HAS2 is seen more in early human development, while HAS3 is seen more in adult tissues. However, there is still more being learned about these enzymes. Some properties of the HA molecules are it has a solubility of 5 milligrams per milliliter in water and a melting point range of 241 to 247 degrees Celsius. The mass varies due to the differing lengths of the polysaccharides, and a key feature of HA is that it can absorb large amounts of water, and this is vital to its overall function. The melting point indicated on the last slide of 241 to 247 degrees Celsius is due to the intermolecular forces of the molecule. The multiple OH groups in the NH group show hydrogen bonding, which are relatively strong intermolecular forces. This means it is harder for the molecule to go from a solid state to a liquid state. The melting point is also a larger range than usually seen for molecules, likely due to the varying size of polymer chains. The varying sizes of the chain also means that the mass of the molecule is always different. The water absorption properties are due to the many OH groups. Hydrated HA can contain up to 1,000-fold more water than its own weight. It also becomes elastic and viscous. The picture shows how hyaluronic acid attracts and holds water through the hydrogen bonding, as well as hydrogen bonding between each monosaccharide. Now that you know more about how hyaluronic acid is made in the body and its properties, I'm going to talk about the different stages of wound healing and the involvement of HA in them. The first phase of wound healing after the skin has been hurt is called the inflammatory phase. Hyaluronic acid synthesis increases drastically immediately after the skin is wounded. Large HA molecules are used as scaffolding by drawing water to the site of injury and allowing other cells that will help with healing to get to the injury site faster. The fragments of HA also bind to fibrinogen, which is a protein that is crucial to blood clotting. The large amounts of fluid being drawn to the injury cause swelling in the area, otherwise known as edema. The inflammation phase is essential for wound repair. However, if it proceeds too long or is cut short, then this is how acute or short-term wounds can turn chronic. After the inflammatory phase comes the proliferation phase. To start, smaller length HA molecules attract fibroblasts to the wound. Fibroblasts are different from fibrinogen talked about in the last slide, though they sound similar. The fibroblasts create more HA and collagen, which is a connecting protein that allows the new cells formed to attach and strengthen the wound. The longer HA chains fill in the areas between the collagen and elastin to form a cushion. Elastin is a protein that makes up most of the connective tissue in the skin. The sign that this stage is progressing well is the formation of granulated tissue. This is the skin that looks red or pink and can still be sensitive as this new skin grows in. This is also the step where if HA was not present, then there could be an increase of scarring in the skin. The final phase of wound healing is the remodeling phase. The key to this phase is time. This is the stage where skin normalizes, but it takes time and depends on the size of the wound. HA is not as vital for this step as it and other wound healing specific cells are degraded in the area as they are no longer needed specifically for the wound healing. It is important to remember, though, that most HA is in the skin, so the amount present at homeostasis will be there. What these stages tell us about wound healing and HA overall is that without HA in the wound site, the wound could become chronic, healing could be slowed, and extensive scarring can form. Hydrocellular foam dressing is a popular way to cover wounds in the medical world today. It promotes a moist wound environment for better healing and prevents outside contaminants from interfering. There was a study done to analyze wound healing in rats. The amount of hyaluronin in the skin at the site of the wound was measured, and some of the rats had hydrocellular foam dressing over the wound, and some just had the film dressing. In the picture, the rat on the left has the hydrocellular foam dressing, and the rat on the right just has a film dressing. The researchers hypothesized that the hydrocellular foam dressing would absorb the wound fluid, and this would then promote wound healing. They created identical wounds on the rats and measured the area of the wound each day for 7 days. The level of hyaluronin in the epidermis was also measured. The researchers found that the size of the wound decreased faster under the hydrocellular foam dressing compared to the film dressing. The pictures above the graph show a visual of the size change each day, and the graph shows the quantitative area of the wounds. They also found greater content of the hyaluronin in the skin of the rats with the hydrocellular foam dressing. The significance of this is that quicker wound healing can have physical, mental, and financial benefits. More research like this can have an overall positive effect in this field. The research that is being done on hyaluronic acid is very important. Wound clinics are one place that can use this research to speed up wound healing and alleviate suffering of patients. Non-healing wounds can be detrimental to people's emotional and mental well-being. Promise has been shown so far with what research has been done on HA. If HA can be further researched to increase the speed of healing even more, then it can be used in a variety of situations such as for combat medics, lessening time in hospitals, and with potentially helping areas that don't have access to clean accommodations and are more likely to get infections from wounds. Medical bills are also very expensive, and with this research, there is a potential for time and money reductions in clinics and hospitals if healing time is increased. Also, if the people can limit these bills with at-home care through certain wound dressing usages, then that will be a benefit as well. At this time, there seems to be conflicting research about the best size of the polymer for wound healing in different situations, so more research would need to be done to finalize that. This is the end of my presentation on hyaluronic acid and wound healing. I hope you enjoyed it, and thank you for listening.